Okay, so here's my outline. I thought I'll give an overview of these objects called normalizing flows, which are used to model probability distributions and which actually have a lot of different uses, both in data analysis and specifically in cosmology, and that's what I'll be talking about. So let me start first by saying what is a normalizing flow. It's a mapping from some initial probability distribution, think of it as a Gaussian, to some complicated probability distribution, which may describe, I don't know, maybe probability distribution of the data or something like that. So this mapping is a flow. So in other words, you map first from here to here, then you map from here to here, and so on. And at each level, each one of these maps, these functions f and their inverse, this mapping is bijective, so you can do it in both directions. Each of these maps is supposed to be simple. Simple in the sense that it can be inverted, and simple also in the sense that we can evaluate the determinant of the Jacobian. And so if so, then we are able to evaluate both the density in, say, this data space X, and so this is, we're going to call this P of X, which is going to be the density in the original space, which is just some Gaussian times the Jacobian determinant. But moreover, we can also draw new samples. Once we have found this mapping, we can draw new samples X by just drawing a sample in this what we call latent space or Gaussian space, and then just passing it through this inverse of this f to the new sample. Okay, so that's the idea.
Sorry if I may ask. So the implication is that each step, this is true for each step, but you couldn't do it all in one step. You need to go the intermediate step.
Correct. So each step might be some simple function.
Yes.
Right. And then which you can invert and which you can evaluate Jacobian. And when you combine a lot of these steps together, then you actually get very complicated functions. And the idea is that you can model any distribution this way. Okay, so there are some completeness theorems behind this that I won't discuss, but these things are actually guaranteed in some sense to be universal approximators. Mm-hmm. Okay, so in one dimension, how this would look like. Okay, first of all, how do we train, as we say, train the flow? What we try to do is we maximize the likelihood. What is the likelihood? People use likelihood, but really it's just a density. This P of X, and you maximize it under these parameters of this transformation. This f has some parameters, free parameters that you fit for, and try to maximize this object. And it turns out this is equivalent to minimizing some distance between probability distributions. In this case, is KL divergence or Kullback-Leibler divergence between the true probability distribution and this approximating probability distribution that we're trying to learn. And so, for example, here is, let's say you have some data that you want to map to a Gaussian. Maybe you start with something like this, and this doesn't look like a Gaussian. But after the training, where you're trying to maximize this object, you may get a function f that looks something like this, and then this function has now mapped this distribution into a Gaussian. That's the idea. All right, so of course, what we want to do is we want to do this in high dimensions and let's say d dimensions, and so that's why we want to do this many times. In one dimension, the problem is easy, and we can do it with a single step. But in high dimensions, the problem is hard, and in general, there is no unique solution. So what we want to do, therefore, is we want to still parameterize this f such that the inverse and Jacobian are easy to evaluate. So there are many different approaches to this, and some of them actually are continuous, and they're based on either ordinary differential equations or stochastic differential equations. And they're very fascinating because they have lots of connections to Fokker-Planck equations and so on, so they're very fascinating also from the physics point of view. But the one I'll be talking about here is one we developed with my student, Biwei Dai, and it's called sliced iterative normalizing flow. And it goes through slices. Now, what are slices? What are projections? Here, the motivation for us is the so-called Radon transform. What is a Radon transform? Radon transform says, there's a Radon transform theorem which says that any high-dimensional density can be parameterized in terms of one-dimensional slices. What are one-dimensional slices? So think of it, let's say you have an object, you want to describe its density. You just project its do projections of the density along different directions. Okay, and then this theorem says you can reconstruct, in this case, let's say two-dimensional image from these one-dimensional projections. So this actually underlies the CAT scan methodology, right? So where you do these projections, you see, then you order them by, you rotate this CAT scan, you get these kind of things, then you Fourier transform this. You do this, then you basically orient this thing around a circle. You have to have a kernel correction, which is just some function of k. So this is very close to Fourier transform. So you get this, and then you do inverse Fourier transform, and out comes the two-dimensional image of a brain. So in high dimensions, why is this hard in high dimensions? Because you have this so-called curse of dimensionality. You will have to do this along so many of different projections that it becomes impossible. All right. So in high dimensions, this is a challenge. The curse of dimensionality is a challenge. So what can we do instead is the following. We can, instead of looking for all possible directions and just averaging them, let's look for just the directions where the deviation between the distribution where we are at and the target distribution is the largest. Okay, so imagine, for example, here the target distribution would be this double peaked thing. Imagine that right now what we have is this blue distribution. So what we can do, we can look at all possible directions of these slices and look for the largest deviation of this one-point distribution function between the two distributions. For example, in this case, we found this direction, and you can see that these two are very different. Now, how do we define the distance? We use something concept called Wasserstein distance, which is originated from optimal transport. I won't go into details, but basically there are nice ways to define the distance between distributions. Okay, so once you found this, then what you can do is you can now map the blue to orange. You find this one-dimensional mapping, this F, one-dimensional F, and then what happens to the high-dimensional distribution is the blue becomes something like this. It's still not the same as orange, but it's closer than it was before. And so that means you can just keep doing this, right? Now you can look for another direction, right? Oh, sorry, what happened here? That was planned. Right, so now you can look for another direction and just keep doing this. And you can stack it together as a flow. And it turns out, this has the same architecture as a typical neural network. First, these projections are just linear operations. So, you're multiplying, you're rotating the data, right? So it's multiplying with some linear algebra rotation matrices, and then you're doing some 1D nonlinear transformation, which you can think of it as a nonlinearity. And so that's, you can think of this as a deep network. Okay, so how does it work? How well does it work? Well, here's an example of generating data in high dimensions. For example, you take this M-ish clothes, you start from white noise, and then you do this, and then after a few hundred of these steps, you have generated a fashion cloth, for example, or a celebrity image or something like that. You can get M-ish digits from this. This is from our paper. This is the fashion clothes, celebrity images, and so on. So these are all high-dimensional examples, which is saying this method works in very high dimensions. We're talking about 800 to 3,000 dimensions. And it turns out that it's actually quite state-of-the-art in terms of the quality of the images. But that's not what we care about so much.
Sorry, I'm going to interrupt again.
Yeah.
What is the definition of dimension? I'm seeing two-dimensional pictures. What's 800 dimensions here?
800 pixels.
800 pixels. Yeah. Okay.
Each pixel, because you're looking at correlations between the pixels, right?
Gotcha. Okay.
So the fact that the data structure is two-dimensional is irrelevant for this purpose. You're really looking at the correlations. Right? So now, if one pixel is this, then what should be the next pixel, right?
Gotcha.
They're correlated, right? In a very complicated, nonlinear way, right? Non-Gaussian way, Yeah.
How many dimensions, how many directions, slicing directions are you going to keep?
No, all of them. I mean, well, in this case, for example, we have a few hundred, right? That's what we're doing here. Okay, right. Another thing that is worth saying is that in this latent space, every position in this latent space is corresponds to something real image. In other words, we are moving between the images along high density regions, each of which can then be mapped to something real. For example, you can do interpolation, right? You start from here and you want to end up here, and anything in between is also, a phase, right? That's one thing to keep in mind. The other thing to keep in mind, these normalizing flows are very successful because they're not collapsing to the existing training data. For example, the nearest training data to this one is this one here, and it's completely different. And the same is true here, right? They're very different. So this is not a collapse. These are not just images that have been there in the training data. It's really creating new images. Yes.
How does this compare to GANs?
Yeah, it's not state of the art in terms of the quality of the images, but the important thing is, I'll get to this next. The reason why we care about is more this property. So this is the sampling property that I was talking about, but the more important property is actually the fact that this is a density estimation. So GANs do not give you density because for many reasons. This is bijective, and we can compute the Jacobian, so we can actually get the density. And here are some standard training data where this method is not state of the art when you have lots of data, like 100,000 samples. But one thing that we discovered is that this particular method is state of the art and has the best results for small training data, 100 to 1,000. It's always the best. Moreover, it's also orders of magnitude faster than standard normalizing flows. And so these are the two properties that we'll take advantage of as we go along, right? And so the fact that this seems to be very powerful for small training data, in the sense that probably has better inductive bias. One more thing I should say, this method also has very few hyperparameters, so in some sense it's easier to use. All right, but let's see what we can use it for. Here's one example. One example is anomaly detection. There was this LHC anomaly detection challenge 2020, where they generated 1,000 PTI events for LHC experiment, 1 million background events, and then injected some unknown signal in there, which turned out to be some resonant signal with some jets and so on. And so what we did was, all they give you is the output of an experiment. So what we did was we ran jet finder, we found jets, we reconstructed their masses. And then what, our approach to this method was, let's do the density estimation in this space, this 4-dimensional space, as a function of the fifth parameter, which is the invariant mass. And let's see if we have some excess density relative to neighboring bins in terms of mass. Okay. Yes, okay, so this is what we're doing. Imagine you have this data like this. Right, this is this mass, and this is one of the 4 variables, for example. You can't really see much here, but what we're doing is we're looking for density in this 4-dimensional space, and we're comparing it to the density in the neighboring mass bins. And if there is a resonance, then it will show up as an excess in this high-dimensional density. And indeed, when we ran this, we got an excess here. And it turns out, this is actually from a few weeks ago. Someone Courier, wrote an article about this, and basically, the bottom line is, it turns out our method was actually the best. So here are the results from this blind challenge. This density estimation, our method, was actually the only one that got the cross-section right. We predicted there were about 1,000 events. We were bang on. You can see basically how everybody else predicted a lot more events. Some of them actually predicted like 15% of the total number of events, because total number of events was 1 million, right? You can see a few 100,000, some of them predicted. So the actual answer was more like 1 in 1,000, and we got it right. So anyway, so that's one application. Yes.
How do you impose the conditionality of that? Because these are conditional.
These are conditional as a function of one parameter, this MJJ, yes, and that's what we modeled as a neural network. I'll talk more about conditional things. All right, so let me move on now to the data analysis, how we can do data analysis with this. So where else do we need these high-dimensional probability distributions? One place where we use them a lot is Bayesian posterior analysis. Let's say we have some parameters y, we have some data x. Typically what we want is a posterior, P of y given x. And typically, actually, what we want is marginalizing this over all parameters except one or maybe two. So we usually present this in terms of one-dimensional or two-dimensional plots. The method of choice is Markov chain Monte Carlo. There are many different flavors of it. I won't go into it, but there are also many issues, and there's a reason why there's so many flavors. The samples are correlated. These are Markov chains. They are correlated. There's a burn-in issue, right? So have you converged or not? And they often need a lot of samples. And as a result, a lot of these collaborations in astrophysics and cosmology, like LIGO, DES, Planck, and so on, most of them actually, they're spending a lot of time running just MCMCs. In fact, probably it's the main use of supercomputer time in cosmology, the MCMC chains. So what we want to do is now approach this with this normalizing flow. And the idea here is let's try and fit this posterior to a normalizing flow, which is normalized and therefore already gives you a posterior. So we want to fit this with some kind of form like this synth. Q of y. Now, the problem, however, here is previously we had samples of the data and we were fitting the density P of x on the samples. In some sense, that's an easy task or easier task because now we have a harder task. We don't have samples. All we have is access to this joint probability distribution, P of x, y. We don't know the normalization, and so we don't know where to place the samples, where the density is high, where the density is low. We don't know that a priori, right? So this is why this is actually a harder task than the one I was showing before. Okay, so what we're going to do is we're going to try and get some approximate density first, and then we're going to keep correcting it by using importance weighting. And importance weighting is basically the idea that if you have an approximate version of some density, then you can apply these weights, importance weights, which are the ratio of the two things that you can compute, and then you get a better thing. And then the other thing is, how do we get this approximate Q? We'll try to do this comparison between the two probability distributions using these last time distances that I mentioned before on existing samples, and then just see how far we get to that. All right, so let me just show you. So there's one more thing that we do, which is we do temperature annealing. We start from the prior and we slowly lower the temperature. So initially only the prior matters, and then we slowly bring in the likelihood. So the basic idea is, let's say the true distribution is 2 Gaussians. At low temperature, blue is the distribution of the samples that we have called. These are these gray points. And red is this fitting this QY, and you can see at low beta, high temperatures, this red doesn't quite fit the 2 Gaussians, but it's, in other words, it's broader. And then as we lower the temperature, then we zoom in onto these 2 Gaussians. So okay, so does it work? Well, this is still preliminary. But this is an example that we recently managed to obtain in 10 dimensions. This is a correlated 10-dimensional Gaussian. This is actually a hard problem in some sense because there are strong correlations. And we got this result. There are 2 lines here, red and blue. Red is the truth, blue is our result. They're indistinguishable. And this it took 3,000 calls. This is a very, very low number of calls for this kind of problem. And we think we're getting some very promising results. The important thing here is this is not a Markov chain. These samples are all independent because they're drawn from these approximate distributions. Okay, and so you can actually draw them in parallel. So in terms of the CPU time, actually, you can do this with this effectively, 20 effective calls. You can parallelize everything as compared to thousands or tens of thousands or millions in some case, right? So, this could have dramatic acceleration properties in terms of MCMCs, but it's still too early to say whether it's going to work in general. However, we did get a very large grant actually to study this further. So I hope we can make some more progress in the future with this. There's a related problem, which is optimization or global optimization. What do you, how do you find peaks of the function, for example, if you want to maximize this? And we can also use the normalizing flows for that purpose. Here, what we do is we draw samples from the current estimate of this density Q, but we also want to put samples where we don't have any samples. In other words, we have two density estimators, one of basically of unweighted samples and one of these weighted samples, and then we compare the two. And these are, for example, this 6-hump, which has two peaks. And basically, the bottom line, you get correct results with about 35 calls. Let's have another one. A double Gaussian, similar story, right? So we, as we zoom in, then we zoom into the right answer, which is here in this case. So this seems to be working. It seems to be competitive with the state-of-the-art methods. Okay, so there is something. There's a view. This thing is really nothing else but a preconditioner for that we are kind of used to in various applications. Now, usually we precondition our data with some Gaussians, and the way to think about this normalizing flows is generalizations beyond the Gaussian. Right? How do you precondition your distribution? How do you correct for the geometry of your probability distribution? And you do that going beyond the Gaussian distribution. And so that's really the idea here. We are simplifying the geometry in the distribution space. So you can think of it also as a generalization of second order optimization methods. Right? In second order optimization, you use the Hessian, the second order curvature, but you assume it's the same, always the same everywhere. Here, one way to think about it is that we have a spatially varying curvature, spatially varying metric. So this has a connection to Riemannian geometry as well. Okay, so let me skip the rest of this. There's one more thing I want to mention, which is, so far I was talking about surrogating the probability distribution. Surrogating means we have surrogated this probability distribution posterior P of y given x with this Q of y for a given data realization x. Now, what is becoming popular is also goes the name of amortizing, and amortizing means, well, let's do this for all of the data realizations at once. In other words, let's learn this P of y given x for all possible x's. Okay, so and you can parameterize this is now conditional distribution, and so this everything, this Q of y, you parameterize it with the normalizing flow, and its dependence on x, you parameterize it with any fitting function such as a neural network. This pre-training is more expensive, but then the posterior can be faster, and applications would be anytime you observe something, anytime you're observing something many times, that's where this can be useful. For example, high-energy physics experiments, obviously they keep doing the same thing, right? So this is really a good example. But exoplanes, microlensing, strong lensing, gravity wave analysis, these are all good examples because you keep looking in the data for the same thing, right? Strong lensing or black hole marks. Okay, and so here's an example, a recent example from Dax et al. It's a German team, and they have done this. They compressed the data from LIGO to 128 features. So the data is 128 dimensional. They've trained now this for 3 weeks. So pre-training is very expensive in this case. But once they have trained, they got nearly perfect posteriors. There's basically, one is the true posterior, and the other one is the approximate posterior. And again, they're almost indistinguishable. They also get very good localizations. So this thing is very promising, but there's still an open question, right? Do we need to do this amortization? Do we need to do this 3-week training, pre-training, or can we do exactly the same thing with something very fast, such as the methods I was talking about before? And there's still an open question whether this amortization is necessary. Okay, so let me now talk about cosmological data analysis. So we want to, ideally, we want to model, as I said, the data likelihood, which is probability of the data given some parameters. And then, once we have this, then we can invert this to get a posterior using the Bayes theorem. Now, if the data are Gaussian, if the noise is Gaussian, then this would be the Gaussian case. Then we know how to write down this likelihood. We have an analytic form. It still doesn't mean it's easy. If we have a noise and a mask, a survey mask, then we have, yeah, we can write it down, but there are these inverse matrices floating around. If the data is, million dimensional, then we have to invert million times million matrix, and this is actually not even feasible computationally. So there are issues even at the Gaussian case. So for example, for CMB data analysis, people don't actually do this full likelihood. They do something called pseudo CL, where they know they have lost some information, but they hope they haven't lost much. Now, as we go to the non-Gaussian case, then there are things that things get even more complicated. One is that the likelihood might not even be tractable. For example, how do we even write down the likelihood of the galaxy data? We don't have a good noise model for galaxies. And the second, the forward model now, let's say you want to predict your data. The forward model, as we say, is a full simulation, maybe Anomaly simulation, maybe even a hydro simulation, because you want to compare the data to the model, and the model itself is very expensive. So what we do instead in cosmology, we don't do this, right? We create summary statistics. For example, we create power spectrum, nonlinear power spectrum. It's a summary statistic. We compute also its covariance matrix, for example, and then we work with that. Or maybe we do bispectrum, or maybe we do Halo mass function, or void mass function, or whatever, right? So a lot of these summary statistics, and then we try to combine them. We have to compute the covariance matrix, and so on and so forth. So it's we have no guarantee that this is lossless. It's probably not. So we have information loss, and we have to build these covariance matrices and so on. So it's hard job, right? And there's a lot of people, including people here in the room, that are working on this. So now the question is, can we do optimal cosmological data analysis? Optimal in a sense that we can extract maximum amount of information from the data. The answer is, well, maybe. Current approaches that we have been pursuing, but also other groups, is that we try to reconstruct the initial conditions. For example, just to give an example, lensing of CMB would be a model where you are able to write down the likelihood. It's a function of, think of F as a CMB field in a temperature polarization. So it has some power spectrum. So this is, its prior, basically. Then think of phi as the lensing potential, and again, it has some kind of prior. And then you have data, and the data is CMB, but also applied some lensing operation on it. And this lensing operation might be nonlinear. Okay, so, and then there's some noise in the measure. So this would be the likelihood. We can certainly write it down, but you can see it's a function of the parameters we care about. Let's say cosmological parameters would enter into this power spectrum of phi and power spectrum of CMB. But it's also a function of all these, what we call latent space variables Z, which are the field, CMB field, and the lensing field. All right, and so if you want to get to the likelihood of these parameters, you need to integrate out these parameters Z. You need to do this integral. But this is easily multi-million dimensional integral, and this is the hard part, right? This is the problem. And as I said earlier, that the other problem is that sometimes we cannot even write down a likelihood, especially when we deal with galaxies. So those are the two difficulties in trying to do the optimal cosmological analysis. And we're trying, but it would be nice to see if there's another way to do this. And so another way to do this is how can we try to learn directly this likelihood, P of X given given Y, without using these latent variables at all. So the pro would be, there would be no summary statistics. We are learning the likelihood directly. Therefore, there should be no information loss. There's no latent space likelihood used, so no marginal integral needed, right? So all of these things, all these deficiencies, then they go away. There must be a catch, right? And there is, the dimensionality of data is extremely high. We have surveys which easily can measure millions or sometimes billions, not so much billions of numbers, but in terms of describing them with a simulation, we probably need to run simulations which are 1,000 cube or more. So it's very high dimensionality of the data. And can we model this with these normalizing flows? Can we create a normalizing flow model for this P of X given Y? Is this even possible? And the answer is yes, it is possible, because we can take advantage of translation and rotation symmetries. And so this is what I will talk about next. This translation rotation equivariant normalizing flows, or TRENF. What's the idea behind here is Just like in standard neural networks, there were neural networks up until 10 years ago. That was the only thing there was. There were these fully connected neural networks. And then convolutional neural networks came along and really revolutionized the field. So convolutional neural networks, they have translational symmetry built in, right? Because they're convolutions. Our task here is to take this idea and first of all incorporate convolutions into this normalizing flow framework so that we have a bijective map and we can draw samples. In other words, we can draw realizations of say embodied simulations. And also it has to be, of course, differentiable so we can evaluate Jacobian because our ultimate goal is probability of the data given the parameters. And second, generalization is that we want to enforce rotational symmetry, which usually convolutional neural networks don't do. So how do we do this? We do these convolutions in Fourier space. So what we do is the following thing: we take data, we Fourier transform, and then we multiply with the convolution operation, which in Fourier space is just multiplication with basically a transfer function. And this transfer function has three parameters that we then optimize for in the training. But the other thing is to enforce a rotational symmetry. What we can do is we can say this transfer function is only a function of the amplitude of the wave vector rather than direction. And so we drop the arrow here, and so this is therefore a one-dimensional function here that we parameterize with a spline. So that's one aspect. Now, once we have found this convolution, we then go back to the real data and we look for its one-point distribution function, and we basically Gaussianize this. We map it to a Gaussian. All right, and that's this nonlinear summation side. So basically, this is the same process that we were doing in synth, right? Except that we are restricting these, instead of the general rotations that we were doing before, here, these transformations are limited to Fourier transforms and the transfer functions, because those are the two operations that guarantee translation and then notation invariance. So the same structure as the previous method otherwise. All right, and then we can do this many times. We can, put together several of these operations. So in other words, if one point distribution function for one convolution hasn't completely Gaussianized everything yet, let's do it again, right? And we just keep doing it until we have hopefully a mapped distribution into a complete Gaussian. So that's the idea. So the good thing is it enforces translation rotational symmetry. Symmetry, there are very few parameters, actually relatively few. We're talking about, 4 or 1,000 maybe parameters. You may be familiar that in machine learning neural networks, they often fit millions of parameters. Here, the number of parameters is much smaller. Training is very fast, and the consequence of this is that we have less overfitting and better generation. We don't actually need that many simulations. For each cosmology, you can think of you just need one or a few simulations. So that's a good thing. And then the other thing is, as I said, it has a normalizing flow structure. And we're training on this log P, which is a standard training. Let's see. Now, as I said before, we typically, these probability distributions have to be a function of P of X given Y. So everything, so the first one, you model with the flow, P of X, you model with the flow. But now if it's conditional, you want to also describe the conditional dependence. And for that, we just simply, where is the conditional dependence entering? Well, into the parameters, which are in these transfer functions and these nonlinear functions. They're both some kind of splines. And we interpolate these spline functions using some kind of neural network. So that's a standard procedure, right? You just think of it as an interpolation between different cosmological parameters. All right, so let me now go to the results. And the experiments are shown, that I'll be showing are just 2D data, just 2D dark matter projections. We also have weak lensing results, but I want to focus on this just because it's easier to understand. And so what we do is, all right, so these are the parameters of simulation. We vary the two parameters, omega matter and sigma 8. And we run an embodied simulation. In this case, we run a fast PM solver. And so that's what we use for training. This TRENF is a 5-layer. We only use 5 layers. And as I said, we don't use that many free parameters. So, less than 1,000 parameters in total. And then, of course, we also have this neural network for this conditional dependence. which, is just something.
Are you perhaps are about to tell us, but what is the question that we're going to ask of these data? That is, where are we trying to get to?
To the likelihood.
The
Likelihood of the data as a function of parameters. Okay. This is our ultimate goal, which, as I mentioned earlier, is an, we always thought it was an impossible goal. We always thought we have to go to the summary statistics.
Right.
Except in the Gaussian case, and even in the Gaussian case, it's hard, right? So this is where we want to get a full likelihood of the data, even though the data is, millions or billions of dimensions.
Yes.
We would like to get full likelihood.
Now 128 by 128 tells us the number of dimensions that you're actually working with. Is that correct?
Correct. In this case, it's a two-dimensional. Yeah. So this is still relatively low, right? No,
Okay.
10,000 per eye, but we can scale this up. This one is probably not so hard to scale up. Okay, so here are the results in terms of the sampling. Okay, these are the training data. So think of this. So here we are varying omega matter going from 0.5 to 0.2 in this direction. So you can see basically how as you go to lower omega matter, you get the spectrum gets redder and you get larger voids and so on. So it's more like white noise here and more red here. And here we're varying sigma 8 from 0.6 to 1.1, and you can see how clustering gets stronger as we go from low sigma 8 to high sigma 8. So this is after the training. These are our samples, and you can see at least by eye they look very similar in terms of the structure. And so you can think of this therefore as a very fast generator of n-body simulations. Does it work in detail? We think so. Here's the one-point distribution function between the training data and our generated samples. They look perfect. Power spectrum looks perfect. Three-point function, this bispectrum looks perfect. So, all of these high-order statistics look pretty good. We can also look at this statistics in the inverted space, right? Because what we are claiming is that we have mapped the data into a Gaussian, then we have achieved a perfect transformation, and then we have learned all the information there is in the data. So here is a one-point distribution in the Gaussian space. It looks perfectly Gaussian. Here is the power spectrum. It looks perfectly white. And here's the three-point function, and there's nothing yet, right? So again, by eye, not by eye, by these statistics, there's nothing. So it looks like we have achieved, perfect mapping. In fact, we can also use other anomaly detectors, including our own brain. For example, here is, if we use the correct cosmology, this is what we map into, and this looks very much like white noise. I mean, our brain again can pick up, the structures, and there's not much going on here in terms of non-Gaussianity. On the other hand, if we had used wrong cosmology, then we would have obtained something like this. In particular, there's this ringing here, for example, which is clearly non-Gaussian. I guess the argument I'm trying to make here is that it is sometimes easier to see if the model is misspecified. In other words, if we're missing something in the model, either some important systematic or some important astrophysics, like baryonic effects. It's in some sense, it's easier to look for these features once you've taken out most of the gravitational and maybe most of the galaxy formation effects out, and then you still look for these kind of things in this latent space. All right, so of course, in this latent space, we may also be looking for some real new physics. For example, primordial non-Gaussianity would be also easier to look for in this map, which we claim is perfectly Gaussian, but maybe there are some correlations which would correspond to some specific three-point function from the early universe and things like that. So for these kind of applications, I believe this is also a useful strategy to go, because we have Gaussianized, we have removed all of the higher order information, but we have also put all of the higher information into this Jacobian. Okay, and so that's what I want to talk about next, which is we have, if we achieve the perfect mapping, we have put all the cosmological information into this density estimator, which remember is some Gaussian times this Jacobian. And the Jacobian has now the information about the cosmological parameters, compressing all of the high order correlations into a single number. All right, and that's the beauty of it. And so what we can do, therefore, if we have this object, the likelihood of the data given the parameters, we can just use Bayes' theorem and get the posterior of the parameters given the data. by, well, basically by integrating this value of the likelihood over in this case, over this parameter space of the two parameters in this case. So what I'm showing here is, first of all, red is the results from the power spectrum, and green are the results from our full analysis. And you can see in terms of figure of merit, we have 6 times more information than we had just from the power spectrum. So that's one thing that's coming out. The other thing is the black star is the true value for that particular simulation, and you want the true star, the true value to be, 68% of the time within the 1 sigma contour and 95% of the time within the 2 sigma contour, right? And for the most part, this is actually happening here. Not for the most part. In this case, actually, it's happening, right? So we get correct frequencies distribution of these parameters. And we get a factor of 6 improvement in the errors. Now, the other thing we can do is we can test this, how well this is working on examples where we know the answer. Gaussian case is the only case where we know the answer. And in this case, this method completely reproduces the correct likelihood. And the error contours are exactly the same as they would have been with an exact analysis. So it clearly works in the examples when we know what the answer is. So adding noise is easy. I'm not going to go into detail, but here we have added noise. Now the errors, of course, expand, but we still get very good results. Now you see one thing is interesting. These contours are not always the same, so it depends on the realization of the data. But nevertheless, even though they're not always the same, the true answer is always within, let's say, 95% contours, at least 19 out of 20 times. So there is, however, a problem in a typical survey. We have a mask, survey mask, right? We have, of course, the boundaries of the survey. We may also have some holes in the survey, and so this breaks this translational rotation invariance, and we have to deal with that. And so the way we're dealing with that is to add some additional layers which are not translational rotational equivariant. For example, here we have some mass data. We have removed half of the area, right? So the data are only in the middle, right? And so this is 50% of the area we have removed. And this is how well we currently do on the latent space, So it's pretty good. It's Gaussian, but maybe not exactly perfect yet. So this is still a work in progress. But here is what happens when you run this analysis. And what happens is we still get pretty good agreement, and figure of merit has dropped by a factor of 2, as it should, because we have lost 50% of the area. So this is promising in the sense that we seem to be still getting correct contours and so on. All right, so the future, in terms of future directions, there are a couple of future directions where we want to go to. First, we want to make this an Eulerian n-body simulation. And we can do this either by adding velocities, in which case we would have 2 of these maps, one for velocities and one for the density, but also just without velocities. We can still map from the initial latent space to the final output, let's say n-body simulation. And in order to achieve, so far we haven't been paying attention to what this latent space is that we are mapping to. It's some Gaussian space. But of course, in cosmology, we know the initial conditions. If you divide the initial conditions by the squares of the power spectrum, you should get white noise. So that is also a Gaussian latent space with no structure. And so it should be pretty straightforward to just modify the training loss to add maybe some L2 loss so that these latent variables that we are getting are actually the variables that correspond to initial conditions. We haven't tried it yet, but I think I would say this is reasonably straightforward to do. If we do that, then it will actually be even better in terms of exploring the latent space for promoted homogeneity, because each latent space variable would actually correspond to a specific scale in the initial conditions. The next thing we want to do is break the relation invariance to account for ratio space distortions. We know that a clustering is not isotropic in redshift space, and so we need to be able to generalize this, but in a specific way, including velocities. Another thing what the one can do is make this into an Eulerian hydrosimulation. I'll show a few slides next how we're doing this using Lagrangian displacements. But this TRENF is Eulerian, so it's on a fixed grid, and we should be able to do whatever we're doing with Lagrangian displacements also on a Eulerian grid. And then finally, once we have this done for several different outputs, we can then also learn the likelihood with several maps of the same area as input. Right? So the ultimate goal is you want to combine, I don't know, KSZ and TSZ galaxies and maybe dark matter, all of the same field. So they're all observing the same data X, but in different tracers. Okay, so just to finish off, this is this approach that we have developed earlier, which is this called using Lagrangian displacements. And the idea here is that you train on a very high simulation. For example, we use TNG, illustrious TNG, and you take some, very crappy low resolution n-body simulation in this case, this fast PM, which is very fast, it takes 10 steps. So it's, it's supposed to be very crappy, but then you further displace particles of this fast PM so that you mimic some high resolution simulation. And this is how well this works on the dark matter. And certainly by eye, things look very good. And also in terms of the power spectrum, they look very good. And, to generate these maps here is about 1 million times faster than, whatever it was to generate the illustrious TNG. So this can really, get you to do very, very fast maps of, I don't know, maybe half of the sky or maybe full sky. This would be important, for example, for CMB experiments and so on, which need CMB map, TSZ maps, KSZ maps, weak lensing maps, CSB maps, all of that, right? What we want to go, we want to try to do this. This was the Lagrangian displacement. We want to try to do this with this Eulerian. And so here, just a few more examples of this. These are stellar maps, really galaxy maps, right, from TNG, and this is how well we have trained this operation on this crappy low resolution initial conditions, ratio 0.5 and 1, and so again, this is very good visual agreement and also very good in terms of statistics. KSZ, for example, these are now, KSZ is a velocity times the density, and so you can see these large scale flows, which correlate the structure, but you can also see these filaments then due to the density. But again, the agreement is very, very good. And finally, this is thermal noise Lodge effect. Again, this is the TNG map, and this is this LDL map. Okay, so let me just conclude here by saying that, well, I'm not going to read all of this, but basically, okay, the two things I want to emphasize. These methods have the potential to enable optimal analysis of cosmology data. But I do want to emphasize, okay, the future directions, we do need to make this realistic. But finally, I do want to emphasize, machine learning is not easy. Machine learning for cosmology is also not easy. I'm not even sure that there are that many success stories yet out there in terms of machine learning. So if you have a machine learning skeptic, you should be. And so there's no guarantee that this will either be optimal or that it will beat standard methods. And again, many people, including myself, we have spent many years, trying to develop the standard methods, let's say, nonlinear power spectrum analysis and things like that. Those efforts will continue, of course, but I would say maybe, well, first of all, this is kind of fun, and perhaps promising enough is worth further exploration and trying to get into this ideal of optimal cosmological analysis with these kind of approaches. I'll stop here.
Thank you, Uros, for this fascinating talk. So, do you have any questions? So we have several questions on Zoom, so maybe we'll start.
Yep. So in the case that you use TRENF and you do some optimal analysis and you get really tiny tight posteriors around cosmological observables, is there a way of validating that posterior besides just looking at like the latent variable space and then checking that it's Gaussian?
I think that one is quite powerful. I really want to advocate that one as because you can, really, you can do summary statistics like these, right? You can just look at it visually, right? Like this. You can actually, run your favorite adversarial network that will try to find something, right? So there are many tools at our disposal to try to see if this latent space is Gaussian. If it's not, then you're either missing something or maybe you have some problem understanding, right? So it is a powerful approach, I think, to look at the latent space and see if things are Gaussian there. And conversely, if things are Gaussian, then I think you have a pretty reasonable, good argument that you have found the correct mapping and that there isn't anything else missing.
We had a question from Christopher on Zoom. So Christopher, could you please unmute yourself and speak up?
Oh, no, I think I was just clapping. Sorry about that.
Question there? There's a question.
Yes, please.
Hi, nice talk. Can you tell us how many fast PM simulation you need to do this particular example here?
Yeah, right. So, we had hundreds of thousands, right? But this is more a function of the grid, how fine you want the grid to be. If you wanted to, I think you could get away with hundreds, let's say, right? It's a two-dimensional grid. You want to populate it well. For each simulation, I would say, maybe one simulation or a few simulations is good enough. Most information is coming from small scales. So you don't need to worry about the cosmic sampling variance on large scales so much, right? And so for this particular case, where most information you're trying to extract is on small scales, it's probably at each grid point, you just need maybe one or a few simulations. And then it's just a question of how fine grid you need to have in order to do, proper interpolation.
And do you have an idea how this will scale with going down to sub% accuracy for the next kind of surveys?
I'm not sure what you mean by sub% accuracy. This is pretty okay. Okay, it's true the grid should be finer maybe, but it's not clear even that, right? Because this thing can be smooth. It's a function of cosmological parameters. Maybe they're smooth enough that you don't actually need a finer grid. So if anything, what happens when you go to higher precision is the contours get more Gaussian, right? So for example, if you look at these contours here, they're quite Gaussian. It's not that we put that in, right? This is what came out. And on the other hand, if you look when we add noise, the contours can be quite non-Gaussian, right? So when we go to high precision experiments, if anything, maybe it's easier to model this for these solutions.
Have you tried to compare this TRENF with traditional there in terms of constraint power?
Traditional is what?
Convolutional neural network.
Oh, yeah, right. So the only comparison we have is on weak lensing maps against the Columbia group, who is the only, almost the only group that is doing this. And on that, we get comparable results, which may be a statement that those approaches also exhaust all the information. And there isn't, but even that would be an important statement, right? Because they are still using summary statistics, right? And so there's no guarantee that they would get all the information. So if this approach, this approach and maybe some other approaches all find the same amount of information, then we probably have a better guarantee that this is the amount of information there is and nothing else.
More questions?
You seem to be quite skeptical on amortized inference.
No.
It sounded like it. When you said that basically in SYN, for instance, you demonstrated that you go after the posterior directly conditioned on one realization.
Yeah.
Right. So in TRENF, you can do something more complicated. Is that because you're limiting it to all the kind of rotational invariant, translational invariant?
Yeah, TRENF is definitely amortizing and surrogating, right? And it's both. So I'm not skeptical of that. Where I am, where I'm not sure is, for example, let's say you do LIGO data analysis or whatever, strong lensing, micro lensing, whether you really need to do this pre-training on all possible data realizations, because that's extremely expensive.
Infeasible in some cases.
And infeasible in some cases, right? Exactly. Now, of course, the reason they do it is, I should give some background. For example, in this LIGO case, where it is, this case here, the reason they do it is this community is using nested samplers, which are extremely slow, you know, millions. I mean, as I said, you know, sometimes just for a single event, like a team spends like weeks. It's unbelievable how much CPU time is being burned in these MCMC samplers. Maybe the method I was talking about before, right? Like this one here, no, this one. Anyway. Not getting there, but maybe this method will be much faster, in which case we don't need amortizing. We could just get this very quickly, and then we would not need these 3 weeks of training.
One question, yes, please.
So I would like to know, Uros, I mean, how do you plan to deal with baryonic effects? I mean, you have been showing that you can do the mapping from M-body to hydro, but we don't probably trust Illustris TNG to really do that analysis to.
No, that's right. That's right. Yeah. So we're doing that now. What we'll do is we'll parameterize baryonic effects. We can take, for example, Illustris TNG versus Illustris dark matter, parameterize that with a single parameter, for example, and have that as a free parameter that we are going to marginalize over, right? So that free parameter would therefore account for some type of baryonic effects, which would go from small, from 0 to large, right? So that's one. And then probably we would need some, you know, a few more of these hydro simulations to span the parameter space of possible effects. But, you know, basically, you know, we would parameterize with a few parameters and then try to marginalize them within the data completely, not taking clues from hydro simulations, but just marginalizing them within the data.
Yes.
Can you also open the black box, so to speak, and kind of extract what is inside TRENF, which is relatively deep in this tool? What are the location of the most constraining layer?
Yeah, so this, okay, first of all, because we use 5 layers, it's not so easy, you know, there's no unique solution, right? So depending on initial condition, we will find different solutions which end up being equivalent at the end, but they are not equivalent at the level of these transfer functions, right? And so what you're asking is there physical meaning to these transfer functions? For sure, you know, for example, the first one you would do is just a PDF, right? You would just Gaussianize the PDF, right? And without any smoothing, right? Without any convolution, right? And then you ask, okay, so then you have gotten rid of PDF. Then, of course, the next one you would do is you would whiten the data, right? In other words, you would remove the power spectrum information, right? And that you can do easily by just taking this transfer function to be square root of the power spectrum, right? Or 1 over that. So those are the 2 operations that we know what they would do physically, right? Now, there's still something left, right? There's still some of these convolutions, and that those are, you know, perhaps harder to understand, but probably we can, you know, we have this information on the shape of the transfer function, right? So in other words, is it large scales, is it small scales, or, you know, what kind of dimension it is, and we have the information on these non-linearities, right? So there is something we can do, because we don't have actually that many layers, only 5 layers, right? So we can certainly put some physical meaning to those things.
But can you do like a PCA analysis?
Well, it's not that PCA gives you any more insight, right? In fact, PCA is a linear operation that we know is suboptimal, right? These are non-linear, and that's why they're so much more powerful, right? And PCA, you know, what does it tell you if you have 5 PCA components? I mean, is there still?
But can you do a PCA-like analysis?
Well, orthogonalizing them. I don't know what you would gain that. I mean, we could, for example, put in orthogonalization constraints on these transfer functions. I'm not sure that's useful. I'm not sure I'll get any more physical insight by doing that.
Please.
So you mentioned that you can get different but equivalent models, like models that really aren't the same but give equivalent results. When you say equivalent, do you mean in terms of the loss, or what? How do you mean equivalent? Because 2 models that are different should give different outputs when presented with adversarial cases.
I'm saying there's enough of this goes into this discussion, is there a global minimum? Have you found a global minimum, or maybe there are many multiple local minima? How do you do model averaging in these situations? This goes into the discussion of Bayesian neural networks and model averaging, right? Which maybe is Bayesian, maybe something else. But yeah, the fact is the training usually does not converge to exactly the same. In fact, we even have, I didn't mention this, but we have a different type of training, which we call discriminative training. And it gets slightly different results and actually slightly better. Let me see if I can find it. So here is an example of two different trainings. Yeah, actually, this is what we're doing. We're training. So far, I was talking about training on P of X given Y, but we can also train on P of Y given X. It's harder because we have to do this marginal integral. So it is harder, but one can do it. And they're not exactly the same, right? If you train on this versus this, but they're almost the same. And here's a comparison, right? So generative is green, discriminative is red. They're slightly different. The shapes of contours are almost the same, but the red is actually slightly better, right? In other words, it fits these outliers slightly better. So, so things like that, right? So questions, what do you train on, but also the fact that there is some noise in terms of what you converge. This is not convex optimizations. You have no guarantee you always converge to the same.
Can you do this for a 3D density field?
Yeah, you can. We haven't done it yet, but yeah, you can.
More questions? Yes, please.
So on your summary slide, you were talking about making this realistic. That is, being able to apply it to real data. In particular, one of the things that you mentioned were masks, and a variant on masks is a selection function, radial selection function. Is that indeed just a variant on the mask, and how would that be incorporated?
Yeah, it is, and the way to incorporate is to break this invariance. Let's get there. So it's this slide here, right? So we introduce basically non-TRENF component. The simple one would be literally like the one you described in 3D, right? That you would put something that depends on the 3D position. And in fact, that's what we're doing here, right? Think of it as we have a mask. Now, what are we going to do with this mask? What we have put in here is we put in white noise. And we said, okay, this mask is going to depend only on this white noise. And this is what we got out of it, right? So it looks by eye, doesn't look so bad, but it's not working yet. So that's one very simple thing you can do, right? But we're doing things that are more complicated. But certainly mask is hard. It's hard, as I said, even in standard methods, right? And so it's no surprise it's hard here as well. Masks are hard, including the radial selection effect.
Questions? Yes, please.
So you're basically filling in the gaps here by some approximate idea of what is missing.
Yeah, it's in painting, but it's in painting which is supposed to be smart, right? So not just you're trying to take account of the correlations, right, between the unseen and seen pixels, right? This will be similar to, in linear case, it will be a window filter, for example, right, which can spill into the unseen areas, right? And for a while as well, and then it just keeps you, then just go to zero. Here we don't want to go to zero because we actually want to have something that looks white noise in latent space.
More questions? I don't see any hands raised. There are no questions on Zoom. So people from Zoom, last chance. If not, then let's thank you.